All right, so using the max, min, shear stress criteria, and some people, this one is generally known as the Tresca. I don't know if that name sounds familiar or not, but basically Tresca just means maximum or minimum shear stress criteria. So basically we use that equation. What was the equation that I gave you? Was tau will be equal to sigma xx minus sigma yy divided by 2 square plus tau xy square, and we take here the square root. Okay, so we do the numerical substitution. This will give us that tau would be equal to what? Basically, we have here 0 minus 0 over 2 square plus tau square root. So one here xy. So we get the same conclusion that tau equals tau xy. Okay, so again, if we look at the equation we derived last time, in that case, the angle at which this is going to happen was given by the expression 2 times tangent was equal to minus sigma xx minus sigma yy divided by 2 divided by tau xy. So this will give you 0 over tau. And remember, this is the same as sine 2 theta s cosine 2 theta s. So basically it means that what we need to solve is sine 2 theta s equal to 0. So same as yesterday, when is sine theta equal to 0? Will be here or here, no? At these 2 points. So we can have over here, for example, 2 theta s will be equal to 0 degrees, which will mean that theta s1 will be equal to 0 degrees. And the second shear will happen at plus 90 degrees. I mean, this is just direct substitution into the equation. So okay, so supposedly next you will have to go and see which one of these two will be the solution. So in this case, it's pretty straightforward. So page 110. So same thing last time, we had to substitute into the normal stress equation. Here we're going to see and substitute. So into the shear equation, so substituting into tau x prime y prime equal to minus sigma xx minus sigma yy divided by 2 sine 2 theta s plus tau xy sine 2 theta s. So you can see right away that this term will be equal to 0. So basically, this is just going to give tau x prime y prime equal to tau xy sine 2 theta s, meaning that for theta s equal to theta s1, what do we have? We're gonna have tau x prime y prime equal to tau xy, because sine of 0 is 1. And for theta s equal to 90. So be careful here. Remember, it's twice the angle. So this is 2 times 0, 0, no? So 2 times 90 would be 180. So this will give you minus tau xy, because sine 180 is equal to -1. All right, so why is this important? Again, now if our shaft, if we observe that our shaft, let's say we are subject a pure torque and it breaks along this way, what would that mean? Is that the failure is due to the shear, no? Yeah? Okay, so if it fails at 90 degrees or 180, which is basically the same, or here would be straight perpendicular, will mean that it is due to the shear. Okay. Okay. Yes.
I'm confused about the sine 0 equals 1 and sine of 1 equals -1.
So guys, sorry for that before, but I rewrote this page here. I don't know why I did a mistake. The sine of 0 is 0 and this is 0. So the same thing as we had on the previous lecture, that we wanted to prove that brittle materials will fail due to normal stresses. We are here, brittle material will fail due to normal stresses. We did solve the problem for pure shear of, let's say, a shunt, and we concluded that if you apply to torsion on it, it will fail at 45-degree angle. Okay, and we say it's because when you apply the twist, it's like if you will shorter or will elongate the piece of shock, and then it will create an normal stress. So if this breaks due to normal stress, it cannot break due to shear. So if we use the maximum shear stress theory for the same problem, it should give us that it should not fail then in that mode. And this is what we get here. So this is basically confirmation that brittle materials will fail due to normal stress. All right, so now in order to make everything clear, I wasn't planning on doing it, but let's just do it. We're going to do the opposite example, which is we're going to assume instead of pure torque, we're going to assume pure tension. Let's say here, pure tension. And let's see what happens. So we take our element here. And this time we're going to submit it just to pure tension. This way. And we're going to be looking at an element over here. So if we amplify that little element, we're going to get that this one will only be subjected to tension. Okay, so following exactly the same procedure as before. What does that imply? Sigma xx, let's say, will be equal to sigma. Let's call this one sigma. Sigma yy will be 0, and tau xy is 0. So as before, we're going to analyze this one using both failure theories. So one, using principal stresses. So if we use principal stresses, the equation we had was sigma 1, 2 equal to sigma xx plus sigma yy divided by 2 plus minus square root of sigma xx minus sigma yy divided by 2 square plus tau square xy. Okay, so we substitute, this is 0 here, this is 0, this is 0. You can see right away that what we're going to get over here is that sigma 1 will be equal to sigma xx, because we have 1/2 plus 1/2, and sigma 2 will be equal to 0. Okay, so by now I hope that you're getting the routine. Next thing we need to find is to determine the angles for each one of them. So the equation that does that is tangent to theta p equal to tau xy divided by sigma xx minus sigma yy divided by 2. So this will give you 0 divided by sigma xx divided by 2, which is equal to sine 2 theta p cosine 2 theta p. So as before, what do we need? So if you want here, you can just say that this is equal to 0. But if we follow the same procedure as before, we need to solve sine 2 theta p equal to 0. So again, this will give us 2 theta p. Let's do theta p1 will be equal to 0. So let me not do the mistake this time. So it's 0 here and here. Okay. So this will mean that theta p1 will be equal to 0, and P2 will be equal to 17 plus 90. So it's the same as before. As for the shear, it will be 9. Okay, so as before, we need to substitute into the equation for normal stress, which would be the same thing as doing the Mohr circle. So substituting into, again, this equation. I think by now we should know them by heart. So sigma x cosine square theta plus sigma y sine square theta plus tau xy sine 2 theta. So in our case, we say that this is 0 and this is 0. So we were left with sigma x prime equal to sigma x cosine square theta. So like always, if theta equals theta p1, which is equal to 0, what are we going to get? Sigma x prime. So this time equal to sigma x cosine square of 0. So this will give you sigma x prime equal to sigma xx. And in this case, this will be the sigma 1, because that was our value here. Sigma principal 1 is equal to sigma xx. So it's the same thing. Okay, we can take the second one. So the second one is equal to 90. So what is that going to give us? Sigma x prime equal to sigma x cosine square of 90 degrees. All right, so this one here, but I mean, it's not direct because remember cosine square, I mean, it is 0, not a problem, but all right, so it's 0. And this will be then, was the second solution here. The second solution, this one is sigma 2. So if we say this one here would be equal to sigma 2. Okay, so basically this one is very simple. Is that if we have this initial state of stress, once we do our stress transformation, the angle is still going to be 0. And the only thing that happens is that you will have this. So we cannot really draw any conclusion for this one. Okay, basically, we started with this and we end up basically with the same thing. Now let's see what happens if we solve the problem using max min shear stress, which is again what is generally referred in textbook as the Tresca. So again, in that case, the equation is tau x prime y prime equal to plus minus sigma xx minus sigma yy divided by 2 squared plus tau square xy, and we take the square root. So if you look at it, this is only the right hand, this term over here of the principal stress. So in this equation, this is 0, and this is 0. So basically, we are left with tau x prime y prime max will be equal to sigma xx divided by 2, and the tau x prime y prime minimum will be equal to minus sigma xx divided by 2. Maybe I should put over here max min. Okay, and as before, we need to determine what would be the angles. So again, this is tedious. So we get tangent to theta sub s equal to minus sigma xx minus sigma yy divided by 2 divided by tau xy. Where this is 0, this is 0. So this gives tangent to theta s equal to minus sigma xx divided by 2. So again, this is equal to sine to theta s divided by cosine to theta s. So like always, we look at the bottom one, because when you divide something by 0, it's not 0, it's infinite. But we can say here cosine to theta s needs to be equal to 0, which will give us what? So again, let me not do the mistake. So the cosine will be equal to 0 here at the top and the bottom. So that means we need to have 2 theta s equal to 90 degrees, which will give us, let's say, the first angle to be equal to 45. And then the second angle should just be the first one plus 90. So that gives us equal to 135. All right, one last step. Now we need to know for which one this one is going to correspond to, which one of the tau max or tau min. So which one will go with this one or this one. So in order to do that, we need to go back and substitute into tau x prime y prime equal to minus sigma xx minus sigma yy divided by 2 sine 2 theta plus tau xy sine 2 theta. this example, these two will be equal to 0, meaning that tau x prime y prime will be equal to minus sigma xx over 2 sine 2 theta. Almost, guys, almost done with this. So for theta equal theta S1 equal to 45, we get tau x prime y prime equal to negative sigma xx divided by 2, which is what? The tau xy minimum. Equal to tau x prime y prime minimum, and then we do the same thing here for the other one. Will be the tau xy maximum. So, all right. Now let's see, hopefully, does that result remind you something, the 45 and 135? Okay, so what does that remind you? From the other day, what did we conclude? Is that if we had, let me just open the file, will be easier. So guys, the reason we did the pure torque and the pure tension is to basically give you an idea about the mechanics of failure for static loading. All right, so there's one more that we're going to look at it, but we're not going to derive it. Since we are here, I think I did tell you that I will give you all the notes with the derivations. So let's see if I have them somewhere. This one, if that I can just put it. Let's see, that one has all the transformation. This is different. This is all in 3D. But this, you see over here, I do all the transformations about A and B. You do the summation of forces. We get the equation that we mentioned the other day, no? Okay. You do summation of force on the Y. You get on the XY, you get the expression for the tau XY, which is over here. Okay. Principal stress is a maximum shear stress. All the detailed derivations are here. Remember, I plotted this one. I told you this is the same thing as in the Mohr circle, but nowadays you could just plot them over here, no? Okay. So I'll give you all this stuff. This is all the derivation of the equation I gave you. Maximum, minimum shear stress. So this is the Tresca. So you take the derivative and you get all these expressions here. Okay. Whatever I give you here. This is, I didn't do it on these notes, but on this one, remember we said the other day that if you apply torque to something, it will be like making it shorter, no? It would change the length. So this is a demonstration. This is the proof. If you are interested, you see by applying torque, this will become shorter, no? Okay. And this is the proof if you are interested. This is for how much the length will change. And that's why when you have a brittle material that you apply the torque, it will break due to the normal stress instead of the shear stress. All right, so I guess here's more examples. I mean, this is the same thing that we have done bar in pure shear. So this should be the same thing. Bar in pure tension. All right, okay, I go into a little bit more detail over here, but not a problem. I'm just looking at the von Mises. Okay, more circle. Probably I don't cover much about this because I'm not a big fan. Circles. I mean, I'll give you this document. Oh, we need to do this, definitely. But before, I want to see if I have the derivation for the von Mises. Okay, so this is important, but this is to go into much detail. Normal stress, principal stresses. Okay. So just remember this, principal stresses will be like a square of the failure criteria. So if you exceed this value, it will fail. If you exceed this value, it will fail, and so on. And this is the maximum strength energy is the one that will give you the, I'm not going to do a derivation again, is the one that should give you the von Mises. Okay. So this is the 3-dimension, 1, 2, and 3. If you apply the forces and you do some math looking at the strains, it gives you that. All right, maximum distortion energy is basically the same thing. We get to, here you have the derivation. We end up to, let's see what would be the equation. Let's see, we get there. I mean, I think we get to this equation here, okay? This is the derivation. All right, so this equation here will be the von Mises, which remember is the one we saw also on the final element, okay? So again, and the shape of this one in the principal stresses was a square or a rectangle. The von Mises will be like this, and actually the Tresca will be this one here, here, a line that will go here, 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 and a line that will go there. I will do it later on. So okay, guys, so far so far it was studied that we studied the principal stress failure criteria and the max mean stress, which we say is known as the Tresca. Failure criteria. So there is one more which is extremely important, which is it has different names. Okay, distortion theory, whatever you want, but generally is known as the von Mises. There is another, I mean, there's infinite number of failure criteria. There's another failure criteria that is known as the von Mises failure criteria, and is given by this equation here. So that once you calculate all the stresses, you find the principal stresses. This is in 3 dimensions, so the 3 should be 0 for all your cases. And this is the yield value square. Okay, I'm going to put here C, class notes for detail derivation. All right, so I'm going to do a figure now over here. This is the really, if you understand the figure, that's all that matters, the figure and the table that I might do afterwards. Okay, so this is static failure criteria. So this is only for static loading. Okay. So what do we have? We have maybe it might just be easier to Google it so you can do the figure. Should have a better figure. Let's see if I can do this. Okay, doesn't matter. So let's see von Mises. Failure criterion. I want to see the figures. I'm sure they're gonna have the figure I want to do. Okay, so they have for these ones, then I'll have for the principal stresses. Okay, but let's do this one if you want for now. All right, so maybe I should do it a bit bigger. All right, it's fine. Let's do it this way. So this will be the, in red, will be principal stresses theory. So basically it's just a box. If you are within the box, your structure is safe. If you are outside the box, it will fail. Then the Tresca is you go a line from here to here, then you go from here to here, you go from here to here, you go from let's see, how was it? Yeah, from here to here, you go from here and here, and in red, and sorry, in green will be the Tresca, which is the max min shear stress. And now the von Mises, let's see if we can get a, I'm not sure about this one. We go from this edge. So you need to go through all the edges of the Tresca with an ellipse, okay? And you see this should be the yield value minus yield value, yield value minus yield value. Okay. So let's see. I have here an orange. So might not be that good doing this. I don't know how good I'm going to be at this. Oh, you see, I already did wrong. We go through. It's not the square of this one. Is to go through the not through the principal, through the Van Tresca. So it really is over here like this. I'm going to do it solid. So it's here. Sorry, here. You go up. You go on this one. You're going to go on this one. You go this one, and you're going to close this one. So it's kind of this one. Forget about this one here. I didn't do a good job. Should be this one over here would be the von Mises. Okay, so on the notes it's not going to be good, but if you look at the video, it's like this. Okay, like this one you see over here, like this one over here. All right, maybe this one is better. And you can say that all this value will be the yield value and so on and so on. Let me try to redo it a little bit better on another page, see if I can do a better job. That way might be a little bit more clear. So, so let's see if I do. So let's see what did we do. We did this one. Let's just do it bigger, everything bigger. Okay, so this is the principal stresses. Then we're gonna have this one here. This will be the Tresca. Principal stresses. Tresca is, let's see, like this, like this, like this, like this, like this. So this is the Tresca slash max mean shear stress. Okay, and they're hard to sketch. Is the von Mises or von Mises. We go from here. Then it will come here. It will come here. It will come here. It will come here. And it will come here. Oh, sorry, we cannot see the image. Sorry, guys. Was putting all my effort, but doing a nice picture, and I think this one is better. And this is the von Mises stresses. Okay, I'm gonna put here C, next page. So again, I mean, why did I do the figures? Because at the end of the day, I think a figure is worth 1,000 words, no? So basically, which one is the more restrictive of all these failure theories? Probably the Tresca, no? Is the more restrictive. Which one is the more open? So it looks like it's like the principal stresses, no? But I'm going to tell you the truth, for ductile material, the method the most widely used is the von Mises. But basically here on the figure, you have summarized the static failure, the most generally used static failure criterion. So for here, this is static failure criteria. Okay, so something that I just want to let you know, just remember this, okay? This is more to remember than anything else. But if you deal with ductile material, and this is the important part when you do any design, if you have a ductile material, 99% of the people and 99% of the cases, you're going to use von Mises stresses. Okay? Then this is really the important part. All the equations are not that important. Okay? This is the important page. Then if you have a brittle material, brittle, but then I'm going to also add composite material. You're going to use the principal stresses. This is what generally is done commonly, okay? Even though, to tell you the truth, nowadays, for the last maybe 20 years, people have been trying to develop a more failure theory, more related only for the composites, okay? But it's still work in progress, okay, if you ask me. So, I mean, if you need to remember something, know how to calculate the loads, then you need to know how to calculate the stresses. If you have the ductile materials, it's a pain because you don't have to find all the stresses to calculate the von Mises, no? Okay. If you have a butyl material, use principal stresses, it's going to be a lot easier. Okay, and the Tresca, I will say use the Tresca when you want your design really to be very accurate, no? Okay, even though you see that between the Tresca and the von Mises is not really that much difference. Okay, so I will tell you, if you use von Mises, if it's safe for von Mises, you can say that will be also, I mean, almost safe for Tresca, no? Okay, the area is very small. However, principal stresses, you can have these end loads that can create problems. So the last type of stresses we're going to look at is the spherical or cylindrical stresses. So for example, what happens if you need to study the stresses into a, let's say, a pressure tank, okay, or a pressure vessel. Again, that's something that at least you should have been exposed to that in solid mechanics, no? But like this class is like an advanced refreshment of solid mechanics. So let's try to do that. And I'll probably stop over here. So this should be page 116. All right, so spherical. And cylindrical pressure vessels. But important over here is that you realize that the analysis we are doing is limited to 2 dimensions. Okay, so again, I'm not going to do a derivation. Why do, no, yes, I'm going to do a derivation since I have it here and it's not long. So we have spherical. So what is spherical? Imagine that you have here a sphere. Okay, so inside the sphere is going to be pressure. So, like always, how do you calculate it? In order, stresses are an internal action. In order to make it external, what do you need to do? Like for the beams, you need to make a cut. Always the same procedure. So we make a cut. Let's say we cut it in 2. Say we get something like that. Get pressure all over this area. Your pressure vessel will have a certain thickness. Okay. And here, you have the thickness here of the wall should be the stress. Okay. So you see, it's always the same procedure. So once you make the cut, what do you need to do? Summation of forces. So let's say over here, we select the X, Y, Z. So let's say we take forces on the x direction. Okay, so you know that stress is force over area. So what would be the force created by the stress sigma 1, sigma 2? What should be the area? Should be the perimeter times the thickness, no? So that would be 2 pi r times t. Maybe I should put on the same, but t also on the same bracket. Maybe it might be more clear. So this is perimeter times the thickness equal the area. So this one is positive. Now minus the pressure over here, P, that would be acting, if you think about it, would be like a disk over here. Okay, you put a disk of pi r squared. And this should be equal to 0. So at this point over here, all right, what is the pressure would be pushing along this disk over here? This would be the pi r squared, no? And we are making the assumption of very thin walls, so you assume that r basically is equal to r minus t, okay? All right, so this is for thin wall assumption. So if you want thin wall assumption. Okay, so if we solve for this equation, we get sigma 1, 2, 2 pi rt equal to p pi r squared. If we solve, you find that the spherical stress will be equal to p times r divided by 2t. Because this one cancel, this cancel, this cancel, this cancel. Okay, so over here, I'm going to put it. I'm pretty sure I don't need to put it, but r is the radius and t is the thickness. Okay, so this will be the spherical stress. Okay, and finally, we're going to do now the cylindrical. Will be the cylindrical over here. So this one is the more classic, like, you know, for the truck, the containers of truck, they don't generally carry a sphere, they carry more something like, which is cylindrical. So I don't know how to plot it, but they will carry something that is like this. Okay, will be more of this type, and then you will have all the stress, all the pressure over here. Okay. So over here, like before, what do we do? We make a cut. It's always the same procedure. So if I make the cut over here, all right. So like before, this will be the thickness. Here, we're gonna assume this is R for thin structure. I mean, you can put just to the end. This length over here would be B. And now this is a bit harder to sketch over here. This should be, because there is stresses like this. On this section over here, but on the section which is like round off, it will also be pressure, no? Or stresses. So, I mean, you know this is curved, so basically it's hard to look at it, but. So let's say, let me try maybe to do another figure, so might help a little bit. So it should be sigma 1. And now through here, this would be the sigma 2. So if we want, this will be membrane. And this one would be longitudinal. But again, it should be pressure all inside this stuff over here. Okay, so if we look at the membrane, okay, we have time to finish. We do summation of forces. Okay, so if we go at the top and the bottom, this will be B times T will be the area of the top section over here, and this one over here. So you need to multiply this by 2. And now, what is the force? So this is area times stress will give you the force, sigma 1. Minus the value of the pressure inside. So basically, what do the stresses do? They need to compensate the force of the pressure inside, no? That action reaction will be the pressure that will be acting on what area? To be again, this would be 2b times r. So it would be like all this square over here. Or if you put 2b times r. And this should be equal to 0. So this is going to give us that the membrane stress will be equal to PR divided by T. Okay, so it will be the membrane stress. And similarly, if you do the longitudinal, you will get kind of similar as before. You will get summation of forces equal to 0. Will give you sigma 2 times 2 pi RT, which are the same as we had before. This is the same as before, basically, minus P times pi R squared equal to 0. So this is going to give you that sigma 2 will be the same thing as before, will be equal to P times R divided by 2T. So if you pay attention, this one should be identical to the spherical, but in this case would be the longitudinal. Okay, so again, maybe I went a bit fast to the derivation, but it's not that important. It's just that you see that it's always the same procedure. You do the drawing, you make the cut, summation of forces over and over. And if you took the aerospace structure classes, it's the same thing over and over. Always the same procedure. Okay. So I'll stop over here.